Now we're going to look at geometric series. As a reminder, you've seen these terms before. Geometric is when each term is multiplied by the same value to get to the next term. So in this particular case, -3 times -3 is 9 times -3 times -3 times -3. And you can look at it as divided by, but we always want to use the multiplication of a quarter, a quarter, a quarter, instead of divided by 4. And a series when the terms of a sequence are added together. So this is the same as plus a -27, etc. Don't be confused by the fact that geometric means multiplying a common ratio and series is adding. So in between the terms is a common ratio, but those terms are being added. The formula gives you 2 books to find the sum of a finite geometric series. I don't particularly know why, because they're basically the same. One is just the negative of the other. They don't give us any particular advantage over the other. One doesn't, like in the arithmetic series, where you have different information that's needed. Just pick one. It doesn't matter at all. The one thing you do need to watch about, especially in this though, is if you have this r to the n is the exponent and not n minus 1. That can come up a lot if you're not careful of what that looks like. Whether that -1 looks like it goes in the exponent or not will matter a lot based on your handwriting. So do make sure you're writing it the correct way here. Find the following series, evaluate it for the first 12 terms. So we have those 2 options, the sum of the first n terms of a geometric series. It doesn't matter at all what you pick again, r to the n minus 1. And r minus 1. And again, r can't be 1 because then we'd be dividing by 0, but that's also completely arbitrary, where we just have the same term over and over again. So u sub 1 in this case is 3/4. R, the value that I multiply each term by to get the next, is going to be -4/3. That negative allows us to switch the signs here. This is plus a negative, if you'd like to look at it like that. And we want to find the sum of the first 12 terms, which means n is 12. So the sum of the first 12 terms, u sub 1 3/4, -4/3 here, to the n. And this is where you need to be careful that it's very clear that it's not in the exponent, r -4/3 minus 1. Grab my calculator, and I already did this out here. So if you put this in, okay, you can use the fraction button right here. You can even put fractions within fractions, so 3/4 times, and then making sure you have the parentheses indicating where there are negatives. Oops. The colors are very helpful here. To the 12th, move over, make sure that the -1 is not in the exponent. Of course, here it won't particularly matter if you put the negative in the numerator or the denominator or in the front, but do be careful that it is there. Rounding that to 3 significant figures is about -9.83. Okay, and that would be done here. Here's some sigma notation. It may help you to write out a few of the first terms and see how many terms there are before you use the formula. Of course, you could just put it into your calculator if it were a calculator question. Starting at 1, 2 to the 3 plus 1 is 2 to the 4, plus 2, so 2 to the 5. You can already see the pattern. And we're all going to go up to 2 to the 3 plus 8 is 2 to the 11th. So if I were looking at this, I see that u sub 1 is equal to 2 to the 4th. R, each term is being multiplied by 2 again. Repeated multiplication is written as a power. And we have 8 terms, 1, 2, 3, 4, 5, 6, 7, 8. So n is 8. And this is indicating the sum. So we want to find the sum of the first 8 terms. We have the formula, and we have u sub 1. I can write it up here again if you'd like to see it. Sub 1, r to the n minus 1, r minus 1. So that's what we want. S to the 8. U sub 1 is 2 to the 4th. R is 2. N is 8. And 2 minus 1. If we put that into the calculator, big numbers, this wouldn't be something you have to do, although it's not particularly challenging. 4,080. Okay. Move that over a little bit so you can see. 4,080. Same thing here. I'm going to use the same method of thinking through. You don't need to if you can identify directly what it's going to be. Starting at r equals 1, 3 to the first times 2 is 6, plus the next one, 3 times 2, or 3 to the 2 is going to be 9 times 2, is going to be, hopefully I wrote it up, 3, sorry, I had written stuff down here. 3 times 2, that's 18. And all we can do for this last one is 2 times 3 to the n minus 3. Okay, so the first term here is 6. The common ratio is 3. We have the number of terms is n minus 3. A little bit weird in the notation here. Don't overthink that too much in this particular case. And then we want to go to the sum of n minus 3 is what it's asking. And using the exact same method here, we're just not going to be able to simplify or really evaluate it. 6, 3 to the n minus 3 minus 1 all over 3 minus 1. This is 2. 6 divided by 2 gives us 3. You could simplify this. It's really a question of whether it's simplified or not. If I multiply the 3 to the first times 3 to the n minus 3, remember those laws would be, both of those are fine answers to this. Converging and diverging geometric series. So converging means they're going apart, that it's not approaching any particular number like diverging is. If I represent this with kind of a little bit of a diagram, if I add the first term, I'm at 1. It won't matter what the value's here. And then I add 2 to that, I get 3. I add 4 to that, 7. What's happening is I'm going to infinity as I add these numbers together. And this particular one too. So the first one starts at 1. If I add 2, 3, take away 4, negative 1, add 8. There's no number other than infinity that this is converging to. It's going away from some particular value. Whereas this one, if I add 1, and then I add a half to that, and a quarter to that, I'm approaching some fixed value. So this one is diverging because it is approaching a finite value. It's an infinite series. A converging infinite. Just wrote that, of course, converging. Exactly the opposite of what I wanted to say because it's coming towards a number, whereas these two are diverging. So when we're trying to find the sum to infinity, if I add an infinite number of these terms, it's a converging infinite series, I will get some value. And that's only true if the common ratio or the absolute value of the common ratio is less than 1, because I'm getting smaller and smaller and smaller pieces. Okay. If I were to look at this with this diagram, I have a whole square. You can probably even see where this is going to go. And then I add a half of a square to it. And then here's another quarter of a square. There's an eighth. And as I fill this in, I'm going towards 2 wholes. So it is converging to the value of 2. Here's the formula also in your formula book for this. And it's only true if, as said, the absolute value of the ratio is less than 1. Because the numbers are getting smaller and smaller, find the sum to infinity. It's a very simple formula. The sum to infinity of this, as you just saw, it's the same one. This is an infinite geometric series. It goes on and on. Is going to, u sub 1, converge to the value 2. The common ratio is a half here. If I were to add an infinite number of these, I would approach the value 2. We're going to talk about limits as we go forward, but for now, understanding this is enough. So this converges. Two other ones. An example, the second term of a geometric sequence is 4, and the sum to infinity of this converges to the number 18. Find the common ratio and the first term of any potential sequences. So I can set up a few different equations. The sum to infinity is equal to u sub 1 over 1 minus r, where r, the absolute value of r is less than 1. But I have neither of those, so I'm kind of stuck. I can use this other information, though, to help me set up a system of equations to find those two variables. The other one is u sub n as before. I'll write both of these that I'm going to use up here. And u sub n is equal to u sub 1 r to the n minus 1. This is from last class. So u sub n, u sub 2 is equal to u sub 1, which I still don't know. R I also don't know. And 2 minus 1 is going to be just 1. So that's nice and easy. I will now rearrange one of these. It doesn't matter which you do. R equals 4 over u sub 1. And then I can sub that back into the other equation. So u sub 1 over 1 minus, here's my new r, and now I only have one variable, u sub 1. I'm going to multiply both sides by this denominator. U sub 1 equals 18 times 1, and that's 32 over, excuse me, that's not 32. That's 9 times 8, 72. We go over u sub 1. Multiply both sides by u sub 1. To get rid of that fraction, I have u sub 1 squared. This needs now my u sub 1 minus 72. This is a hidden quadratic. So to solve quadratics, make it equal to 0. I'm very much struggling with that. There we go. U sub 1 plus 72 equals 0. And this is a nice, easy thing to factor. So I'm going to solve this by factoring. You could use the quadratic formula, or for now, you could use your calculator. We'll talk more about them going forward. But negative 6 times negative 12 is 72, and negative 6 plus negative 12 is negative 18. So the two values here, that will give me 0. U sub 1 could be 6, or u sub 1 could be 12. And if u sub 1 is 6, here's a nice equation that I have for r. R is 4 divided by u sub 1, so that would imply one of my ratios could be 4/6 or 2/3. And this other one would give me that another ratio could be 4 divided by 12, or 1/3. So these would be the possible two u sub 1 and r values of those sequences. And they are both converging because the absolute value of these is less than 1. And if you were to check them, you would find that the sum to infinity of both of those is 18, and the second term is 4. Last one, show that a geometric sequence with u sub 1 equaling 4 and u sub 3 1/9 has two possible sum to infinities, and find them. Okay, well, the sum to infinity is u sub 1 over 1 minus r. Okay, absolute value of that has to be less than 1, so we'll show that it has it. The first one, u sub 1, we need r for these. So I can use that other formula for the sequence. U sub 3 is equal to u sub 1 times r to the 3 minus 1, or 2. And if you solve this, you get 1 over 36 is equal to r squared. And the square root of 1 over 36 is plus or minus 1/6. And because the absolute value of both of these is less than 1, then you have that the series converges and there's a sum to infinity. So this is the first thing we need. So r is plus or minus 1/6, and both of those have sum to infinity. So the first sum to infinity would be if u sub 1 over 1 minus positive 1/6. 1 minus 1/6 is 5/6. And 4 divided by 5/6 is 24/5. So if r is positive 1/6, then we get that the sum to infinity is 24/5. And the other option, if this the ratio is negative 1/6, then you can simplify that to 7/6, and we get 24/7. So those are the two possible sums to infinity.